All right, so today is fashion day with our Change of Dummy Proof t-shirt. So, I have some homeworks to give back. I have actually graded. You handed it in last night, and here it is. Here's your first milestone of your project, all graded. And I must commend you. Everybody did a superb job. Now, what I'm handing back is, I'm not handing back any of the, I didn't print out any of your source code, but I looked at all of it.
Wait, whose is whose?
You can look up at the top, see what the number is, okay? So what I did is I ran everybody's program through a test suite, and I output the results of the test suite. And everybody did a really good job. So we're really doing well. I commend you.
Is your mic working? Is your mic working?
Yeah, I already did a sound check.
I can just see it not working.
Yeah. Okay, so, I assume that there's no questions about this homework that I'm handing back because everyone did really well.
Good job, everybody.
Good job, everybody. Not only that, but everybody had their name and the date and the assignment number at the top of every file. Which I think, well, you just copy-paste. Just copy-paste. Right? Well, there's nothing compared to what's coming up.
Very first thing I did.
Yeah, right.
Well, you can put your name at the top of one. Oh, no, never mind. Was
And
it
then
refactor? Just your first name.
How can you
find a way to make it
You just
default a heading at the top?
Yeah.
You can.
I'm sure there's a way to do
It's
it.
kind of their default thing is very hard to figure out.
Yeah, okay, now, so what I'd like to do today is we have an exam coming up on Thursday. So, I'm not so sure that we're going to I don't think we need to spend time on actually doing the reviewing, other than just tell you what's going to be on the exam, because I think the material is all fairly straightforward. So let's go over what's going to be on the exam. Okay, first of all, what I recommend that you do is you review all of the exercises since the previous exam. Okay? And so, and the main thing that we've done, the homework exercises, yeah. And the main thing that we've done is we've done symbols. Okay? So you really need to know how to do, how to translate. So there will definitely, I'll just tell you right now. You need to know how to translate from assembly to machine, from ASMB, what level is that?
5.
5 to, what is it, ISA 3? ISA 3. Okay, with symbols. Okay, so that's what's different. So, and then you also need to know how to populate the symbol. You have to know what the content of the symbol table is, right? So the idea of what is this, at the bottom of the list, when you do a listing, when you look at the bottom, there's a symbol table, and you need to know. And actually, let's review that a little bit. What is the value of a symbol? In general, what is the value of a symbol?
Address?
It's an address. It's the address of where that code is going to be loaded. Right? There's one exception to that rule. Do you remember what the exception to the rule is?
Branch or something?
No. It's one of the dot commands. Oh, yeah, okay, so we are reviewing. That's fine. It's one of the dot commands. Do you remember one of the dot with one of the dot commands, it's the exception to the rule that a symbol is an address of where the code. All right, let me give you a hint. It's the dot command that doesn't produce any code. Because it doesn't produce any code, then the value of the symbol can't be where the code is, because there's no code. Do you remember which dot command doesn't generate any code?
Block.
No, dot block generates code.
Dot in?
Well, dot in kind of corresponds to the ZZ Sentinel, Starts with an E. Ferris Bueller. No.
No.
It sets the symbol to the value. It
Equates.
equates. It equates. Okay, so I don't want to write all this stuff down. This is all review anyway. So remember, in general, a symbol is the value of a symbol is the address of the code, the first byte of the code that's generated by that. But the exception is the dot equate. So dot EQUATE. All right? In that case, the equate just equates the symbol to the value. Are you with me? All right? And now, here's another one. Here's another big thing that we started doing that we hadn't done before. You need to know how to translate. So let's review some of the principles for translating. And what we mean by translating is we mean translate. Now this was Assembly 5 to ISA 3, but there's another translation that you need to know how to do, and that's translate from HOL6 to ASMB 5. Okay? Now, so HOL6, this is C++. All right, so let's review a couple of the principles of how to do a translation. So, how would you translate? How would you translate C out, quote, double quotes, or C out, blah blah blah. I mean, you know, the output thing, and then double quote, and then hello world.
The character output?
No, not with a string. You wouldn't do character output. What would you do? It's been a while since we've done these. It's been a while since we've written these assembly language programs.
I know you can make a symbol that's like a message.
Yeah, message one. But then what's the actual instruction that does?
Is it an output?
It's not the trap.
No.
Yeah, it is a trap instruction. Yeah, yes, it's stro, S-T-R-O. So a stro is how you would output a string with a message. Are you remember that? And then how would you translate cout ENDL, inline?
The message would be bash n. And then
you
put the character back in.
Yeah, but that's the line. There's a better way to do it than that. There's a more
Line feed.
Oh, bash n is the new line, is the line feed. But how would you just output that single character?
The
The new line. How would you output the new line? In other words, how would you translate this? Cout ENDL. There, how would you translate that?
Caro.
Character output what?
Bash n.
Bash n, what addressing mode?
Direct. No, immediate.
Immediate, okay. As opposed to having that message be the start address of the string. Are you with me? Okay, so that's how you would do that. And how would you output, how would you translate an assignment statement? So for example, what if you said this? Alpha, in C++, what if you said alpha gets 5, no, not 5 times, that would be, gets 2 times alpha plus 3.
Is that
2 times alpha plus 3. How would you translate this?
to use a symbol for alpha?
And alpha is a symbol. Let's say it's an int. Actually, how would you translate this? Let's go back, let's go up a thing. How would you translate this? Int alpha. Yeah, how would you translate this?
Just alpha colon.
Colon, alpha colon.
Whatever the address is.
Well, no.
dot block.
This would be dot block, how many?
2.
2, because an int is 2 bytes. Is everybody clear on that? So this would be alpha, what did we just say? Yeah, alpha colon dot block 2. That's how you would do this. Now, how would you do this? How would you do this assignment statement?
To use the
Don't you do
register.
the rotate?
Not rotate, but how would you translate this?
Arithmetic shift.
arithmetic shift left. Arithmetic shift left is what doubles. So now how would you, so what would be the sequence, what would be the assembly language statements to translate this?
So arithmetic shift left.
And that's not the first one. Before you can do it,
You have to add. No, you don't.
you have to get this into the where?
Accumulator.
You have to get this in the accumulator. So what would it be? Load accumulator,
Alpha.
alpha, comma,
Immediate. Direct.
direct. So this would be load accumulator, alpha, direct addressing, and then what?
Arithmetic shift left.
Arithmetic shift left, which is
ASLA.
ASLA,
Alpha.
accumulator. No, that's a unary.
that's a unary.
That's unary. So ASLA, and then what?
And then add.
Add accumulator, 3, immediate, very good. And then what?
Accumulator,
Store accumulator, alpha, addressing mode,
direct.
direct.
Oh boy.
Yeah?
But
And-
this would be impossible without assigning a value to alpha before, right? So there would have to be.
Well, alpha, well, in the C++ program, you would have to say int alpha. And when you said int alpha, that's where you would define alpha. It would be alpha colon dot block 2.
But wouldn't we have to set alpha as some value? Because that wouldn't make sense if it was.
Well, oh, I see what you're
That's all I'm
saying.
saying.
Yeah. In order for, well, but look, when you're translating, that doesn't
It doesn't matter.
that doesn't matter. The compiler would just translate,
And then it would.
you would just translate it, and then it would be meaningless. Yeah. Are you with me?
So we're just
Now,
translating.
we're just translating, we're not anticipating what the execution would be.
Okay.
You should be able to translate an incorrect program.
Okay.
Is everybody clear on how to do that? Now, do you remember how we did constants?
It's a const, right? It's,
Yeah, but how do you translate a const? Remember we had so in C++, what did we have? It was called like bonus, safe. Suppose you wanted to have how would you do a constant 5 in C++? You'd say what? Const, int, bonus equals 5. So how would you translate this?
Is that the dot equate?
Yeah, that is the dot equate. Right. Oh, so I lied. We are reviewing.
So you have bonus.
So we're doing lots of review here.
Bonus dot equate.
Bonus colon.
And then
Dot equate
5.
5.
and then every time you call
And
that-
then if this were bonus, if this were, instead of being plus 3, if this were plus bonus, then you would load accumulator alpha, direct, arithmetic shift left.
Yeah.
But now what would you do?
Add accumulator, bonus,
Immediate.
Yes. Add accumulator bonus immediate. Very good. You guys,
But we added 3 immediate too. Is that correct?
yes.
Because it's not the address, it's the value.
It's the address because the symbol, the bonus, yeah, the value of bonus will be 5. It won't be the address of where the code would be because there's no code is generated.
Right. Weird.
Are you with me? Yeah. Oh, so this was good review.
Will we have any questions just like the ones from before? Like I know we'll have to use what we learned before to do the new stuff, but will we have stuff just on old things from the first test?
I won't ask you. Well, you might. Yeah, yes, because whenever you do this, you need to know how to do the information representation.
Yeah.
You know, if I put a negative number in here, you're going to have to know what the 2's complement representation is, and it'll be like FF something, you know. Are you with me?
Yeah.
So, yeah. Yeah, I mean, you might need to know how to do stuff that we learned before. Do you see, are you with me on this?
No, it's just
Because-
we haven't done it in like 2 weeks.
I know. Oh, 2 weeks.
Oh, yeah. It's been a month.
I know.
That was a long
But this is good. This is how you remember. You get away from it, you go back, review, you do it again.
This is your teaching system.
Huh? This is kind of like a spiral. They call this a spiral approach. You know, come back to it after it's been gone a while. Okay, does everybody see how that works? I mean, so, and then also, you know, it's a von Neumann machine.
Fetch, decode,
It
increment.
execute, repeat. And what can a von Neumann machine do? It can fetch a what?
Information.
Instruction.
It can fetch an instruction and then muck with it. Just because you have symbols doesn't make, you know, the underlying machine is still a von Neumann machine. Right? Are we good?
Yep.
And then, so that was the chapter 6 material. Now, and then all of chapter 7 up until where we are now. So all that stuff with finite state machines. But here again, none of this Java. I won't ask you anything about the project, the Java. I won't ask any Java coding. But finite state machines. So what are the 4 parts of a grammar?
But really, the only coding we're gonna have then is more the translation.
Yes. Yes.
Because the only code we've written has been the Java.
That's NTPS.
Because we won't have to do like a
Non-terminal,
Terminal.
terminals, production, rules of production,
Rules of production
and the start symbol. Okay.
And the non-terminal and terminal are alphabets.
Yes, non-terminal alphabet and terminal alphabet. And what is the start symbol? It is a what?
Non-terminal.
It's a non-terminal character. Okay. Oh, that was a pretty good review.
on the finite state machines.
Yes.
The non-deterministic just means that
Good. Let's review that. Finite state machines.
I get
Finite state machines. Okay, so let's review. What is it? What is well, I could say, what are the parts of a finite? Well, we never did bullet point that. You know, what are the parts? But I mean, basically, it's a set of states, a set of transitions, it's a set of a subset of the states, of the final set of final states. There's a start state, transition on alphabet, etc. Okay, so, but the important thing is you mentioned, you're asking, what's the difference between a deterministic and a non-deterministic finite state machine?
Simplified.
No empty transitions.
Okay, first of all, right, a deterministic machine can have no empty transitions. If it has an empty transitions, automatically it's a non-deterministic. But just because it doesn't have an empty transition, it could still be non-deterministic.
You can only have one
No choices.
no choices.
Yeah, no
transition
choices.
Leaving any single state.
Yes,
No.
no liberty.
Can it have multiple transitions, but just not the same one?
Yeah, right.
As long as they're not the same transition.
You cannot have,
If you give a character, there's no choice of which direction to
yeah,
go. Once you get the
yeah,
Given a character.
yeah, let's try to just be more
succinct.
succinct and specific. You cannot have a transition from one state to two separate states on the same character. Are you with me?
Can we go over taking out an epsilon transition?
Yeah.
Taking out.
Yeah, and how do you eliminate an empty transition? I thought you were in finite
Yeah,
state
but-
automata.
We overthought it and got all confused.
What?
Remember we had the huge discussion on it the day
Okay.
that it was due?
A to
Okay,
B.
We overthought
okay.
And C, I guess.
Okay, so if we go, here's the empty if we have an empty transition from here to here, and we have a, here, and let's make this be
Some
a,
transition.
and then we have a transition from here to here on B. Oh, I remember the discussion we had. You guys wanted to flip it around and say, what if you go for B and then the empty transition? But then you'd be eliminating B instead of E. Yeah. Yeah. Okay, well, okay, so here's a quick review. How would you eliminate, well, let's do it like, here, let's do it like this. Let's do B
Sure.
and here, C. Okay? All right, so here you go. How would you eliminate this empty transition?
You'd get rid of it.
Final state.
You just erase
You need
it.
a transition.
Is there, that we got rid of it?
You need a transition from the first state on B to the top
On
right.
B to
state.
this one. So what you would do is
And similarly
B,
for C.
and because there's an empty transition from here to here, but a transition on C from here to here, that means that you could go from here to here without scanning anything, and then go from here to here by scanning a C. So you can get rid of this if you just start here and scan a C.
And the first state has to be final.
Right.
And
Well,
now,
if
if
the
this is a final state, then you have to make this be a final state. So there it is in a nutshell.
But if we had to
Now you have to get rid of the
if we
empty
had to
one.
simplify it,
Well, it depends on if this is after you get, oh, and then we've crossed out this.
because now there's no way to get to that middle state.
Well, I didn't draw the others. If there were some other one coming in here, this might still be accessible.
Okay.
But if it's inaccessible, you can just get rid of it and all the transitions from it. Was that good? And you understand why? Yeah.
I have a question.
Mm-hmm.
If there's only an empty transition going from a state, is it still non-determinate?
Yes. Oh.
Just an empty transition.
Wait a second.
Well. Oh.
Is it deterministic? Is that what we're
Well, what he's saying is, suppose I have a,
Just like this example.
actually, just like this example, if this were like, you know, and that was the only thing you
Oh.
had.
So there are no choices?
Because
You
there's
just
no B or
automatically
C.
skip to it,
Before we put the B and C in there.
according to the rules, no.
Well, but then according to the other.
No, it's non-deterministic because you don't know if from going to, well, because see, if this went C to here and C to here, this would be well,
But that part isn't.
but what
that
you're
part
saying is if
deterministic?
this were just like, well, well, here's why it's difficult for me to answer that question. For every non-deterministic machine, it is possible to construct an equivalent deterministic machine. And so the question is whether this is non-deterministic and we made it deterministic after we got rid of the empty transition. Do you see what I mean? So I will say, yes, it's non-deterministic just to keep our rule hard and fast.
Okay.
But if you eliminate the empty transition, that could become, it might. Just because you eliminate the empty transitions doesn't guarantee that it's not, because non-deterministic, because somewhere else there could be some non-determinism,
Right.
even without the empty transition. All right? Well, this was a good review, actually. Okay? Any more questions?
Perfect.
Are you gonna give us problems like we had in that one homework assignment? Where we had to devise specific finite state machines?
Maybe?
Oh, that was hard.
Those
That
were
was
kind of
very
fun.
hard.
The first time I did, I was like, this was so easy, but
Yeah.
it's all of mine were not.
It's easy to make a mistake on those if you don't think
Right.
Oh, yeah,
through.
that's right. You corrected me on that one.
Yeah.
Yeah, what,
All right?
what did we do wrong? I should remember
We
that.
forgot one state, one line.
You sent it back to the beginning when you should have done.
Oh, I didn't need to.
You didn't need to.
All right. So now I know students don't like to do this, but what we're going to do is we're going to forge ahead and we're going to cover some material that's not going to be on the test on Thursday. And let's, now you're going to have more questions to stall me?
This was serious, because in the last test, there was a lot of stuff that we had to like specifically know. Is there any stuff like that on this test?
Oh, yeah.
Because like last time we had to know the 7 levels of abstraction,
Well,
and
We're supposed to still know it, probably.
well, I mean, now that you know the 7 levels of abstraction, I mean, we use that all the time, right?
Well,
not as much.
I mean,
I like the prefix chart.
Do we need to know table lookup?
you know, like I said, I'm not going to ask you any coding techniques,
What
so
about-
I won't ask you any. I won't ask you to code table lookup or code direct code.
What about
So the
being
answer is
able-
no.
What about being able to draw a state transition table?
Oh yeah, you should know how to do that. Given a diagram, draw the table. Given the table, draw the diagram. But that's so
Do we need to
easy.
know what
That's so
nibble is?
easy. Come on. A nibble? N-Y-B-B-L-E?
Isn't that like
What are the
one
X and
byte?
Y?
What is a nibble?
It's
No,
half-
4 bits.
4 bits.
4
Oh,
bits.
4 bits, 4 bits.
No.
It's half a byte.
What are the X and Y coordinates on a state transition table?
What?
We were just talking about state transition.
State transition table,
Yeah.
actually here, well,
Let's draw the one for that.
We do those a lot in organizations.
the way the state transition table works is like this. What you have on this side are states.
Current state.
So this would be like, yeah, current state, like A, B, C. And then what you have here is you have terminal symbols. So this would be like,
B, C.
yeah, let's say X, Y, Z. And then what goes here is a state.
State that it
Yeah.
would end in. So-
So what this means is that if you're in start state A and you have a transition on this
On that.
character, the next state will be B.
Okay. I always want to put both states here and have the transitions in the middle.
No.
It's wrong.
Because you look up, because when you look up the table, it's given the state, given the current state and this, what is the next state? So in the body of the table is what you're looking up. It's what the table gives you. Are you with me? By the way, this is the way we do it in computer organization also.
Yeah, we work.
Okay? All right. Any more questions?
The parsing problem? Do you know about that?
What is the parsing problem?
If you have a proposed sentence to a grammar, to a derivation are not valid. That's what it
Yeah, then the parsing problem is to draw the syntax tree, is to construct the syntax tree or the derivation to show that it's valid.
Okay.
That's as opposed to just generating an arbitrary valid sentence in the language. So with the parsing problem is you're given a proposed sentence in the language and you have to figure out whether it can be, whether it's in the language or not. That's a completely different problem from just generating an arbitrary string of valid sentence in the language. Oh, language. What is a language?
A closure of its alphabet?
Yeah. Oh, no, it's not the closure.
No, it's
No. You're very close, but no
Subset.
cigar.
Subset.
It's a subset of the closure of its alphabet. A language is a subset of the closure of its alphabet. Oh, that was good. Okay, are you ready for the demo? Okay, so now what we're going to do is let me give you a previews of coming attractions. Thursday is our exam. Monday you have an assignment due. It's one small written assignment, but here's what it is. It is to design the finite state machine for the parser of your project. Now you remember we said, now what are the 3 stages of translation, of a translation program?
Lexical analyzer.
Lexical analyzer, parser, code generator. And we said that lexical analyzers can always be based on what? Finite state machines. For translating from a higher order language, the parser is generally based on a what?
Grammar.
On a grammar. But for our situation, since we're just translating from assembly language, we can base our parser on a what? Finite state machine. And what you just did for the first milestone of your project was you implemented the finite state machine of the lexical analyzer.
Now we do the grammar.
Now you're going to do it's not a grammar, it's the parser, okay? But it's going to be based on a finite state machine. And I'm not giving that finite state machine to you. You're going to have to design it.
Are we going to use direct code again?
Oh, yes.
Technique?
So-
Absolutely.
Last time we had to look at this diagram.
Yeah, and implement it. Now you have to come up, now you have to make the diagram. Are you with me? Now, in order to give you some guidelines to do this, and this is always a little bit confusing, but in order to give you a guideline on how to do this, I'm not going to give you a language that's similar to Pep 8 assembly language. I can't, because if I gave you that example, you'd just be fill in the blanks, right? So here's what we're going to do. What we're going to do is the last big example in chapter 7 of the book is an example of a translator that translates from a fictitious language to another fictitious language. Okay? And these two languages are designed solely to illustrate the language translation techniques. Are you with me? And what are those? Which one is the source and which one is the object?
The input and the output.
Yes, the source is the input and the object is the output. And what we're going to do now is what I want to spend the rest of the class time on today is first off we'll do a demo of figure 7.35 in the book, only this is going to be the Java version of it. And this figure 7.35 is a program that translates from one language to another one, and it uses this technique of having the lexical analyzer be a finite state machine and the parser also being a finite state machine. So you can see how one finite state machine feeds a stream of tokens into another finite state machine. But you understand, though, that your finite state machine for the parser will be completely different because the languages are completely different. Are you with me? So it's going to be up to you to be able to make that transition. Yeah? All right. Are you ready for the demo? Okay. Here we go. Okay, so here's our demo, and we'll just start right off the bat. I'm going to, this is already the, what do they call it, the main project, yeah. Okay, so that's already, and it's figure 735, and here's what happens when you run it. Now check this out, you guys. Whoa, now what does the button say? Translate. Now, check this out, sports fans. Here is the source program. Now, before we click translate, let's inspect this language. Let's inspect this program. The first line of this program says set parentheses time comma 15. Are you with me? Mm-hmm. And the second one says neg parentheses time. And the next one says abs parentheses time. That stands for absolute value. Okay. And the third one says set accel, that means acceleration, to 3. And then set, and do you see the rules of the language? Can you kind of visualize what the rules of the language are? It's like the first thing has to be like some kind of mnemonic, and then it has to be followed by a parentheses, and then it has to be a parenthesis, and then it has to be, and then it could either have how many arguments? Some of them only have one argument, but others have 2. And if it has 2, it's separated by a comma, and it ends with a paren. Are you with me? Okay. So, and what do you suppose mul t squared comma time means?
Multiply t squared by time.
Yeah, and put the result where? In t squared.
Right.
See, that's kind of what that means.
I see. By time.
Yeah. Yeah. Okay. And this div position 2 means actually, check this out. When we click translate, now the object language is going to look like this. Now watch this. Are you ready? Drum roll. Boom. Now look, there's 2 outputs here. One says object code. Now the object code is the output of this. So how did it translate set time comma 15? How did it says what? Time colon equals 15. And how did it, up here, how did it translate neg parentheses time? It translated it to what? Time gets hyphen time. And how did it translate absolute time? Time gets vertical bar, time, vertical bar. And how did it translate set accel 3? It translated that to accel gets 3. Are you with me? Now, I'm assuming from this that you can understand what the rules of the language are and what the finite state machines kind of look like, all right? So now that you've done a tokenizer. And set t squared time, that's t squared gets time, mul t squared time, t squared gets t squared times time, da-da, da-da, da-da. Are you with me? Not only does it do this, it also does a program listing. Now, what is the program listing compared to what we had up here in the original?
It's all.
The spaces are gone away.
It's all in the correct cases. It has a canonical, standardized output, blah, 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 blah. Are you with me?
Mm-hmm.
Now, you guys, here is what you are going to do for milestone 2. Your second milestone, you are going to do just the program listing. That's your objective. That's your milestone 2. You will do a program listing. Okay? Now, of course, the program listing is not going to be the hexadecimal code generation. You know, it'll just be the same thing that you did here. You parsed it, and it'll just be echoing it out, but just in a nice format. Now, are you with me on that? Does everybody see?
That's how we do a parser without doing the code.
That's how you, that's how you're going to do the parsing without doing the code generation. Are you with me? So that's milestone 2. Question?
The things in the parentheses, what are those, arguments? No.
Yes, these are arguments. In fact, we will call them arg. And you'll see in the code we're going to name them arg, ARG, because they are arguments.
Okay.
And some instructions in the source code only have one argument like this, but some have 2 arguments like this. And by the way, check this out. An argument in this case, the second argument is a symbol, is an identifier. But in this case, the second argument is a what?
No, a digit integer.
It's a constant.
Right.
Yeah, it's a decimal constant. Are you with me? But what do you notice you can't have in the first argument? You can't have a constant in the first argument because what that gets it wouldn't make sense to say 3 gets whatever because 3 is a constant.
Right.
So that's one of the rules of the languages, you see.
In
So you can have the 2 here, but you can't have the 2 here.
in the parser itself, the arguments need to be, those are case sensitive, right? They should be. We don't have to change that. when we're-
Okay, now the reason I'm doing it like this is to show you that the reserved words here, the mnemonics here, are not case sensitive.
Right, but what about the arguments?
But the arguments are case sensitive. Oh, that was your question. Absolutely. Absolutely, the arguments are case sensitive. That's, yeah. And that's the same way it is in
Any language.
any language, yeah. The identifiers, you know. Yeah, that was a good observation. Now, so does everybody understand? So now, you can surmise the rules of the language from this, and you can see that we have this, you know, program listing. It's all pretty printed and everything's all right. And now the next thing we want to do. So now let's clear this. Okay, and now for my next demo, what we have is a bunch of input that has errors, and we have to see how your program is going to handle these errors. Now, obviously, if there are syntax errors in your source program, you can't do what? You can't generate code. Yeah. You can't generate any object code because it's syntactically incorrect. So what let's do to see how this, to understand how this program works, let's go through each one of these. Let's go through each one of these statements and see what the error is. So what's the error here?
2 commas.
2 commas. What's the error here?
Only 1 parameter.
Only 1 parameter. Set requires 2 parameters. What's the error here?
Sit isn't a method.
Sit, yeah. Somebody misspelled. The user misspelled. It's not one of the ones that when you look it up, right? Oh, and by the way, what we're going to do is these are going to be the lexical analyzer. This sit is going to be okay for the lexical analyzer. It's when it gets to the parser and it looks up in the table that it will. Yeah, are we good? And what about this one?
Comma before a paren.
Comma before paren is not allowed. And what about this one?
Missing a paren.
Missing a right paren. And what about this one?
Constant.
A constant as the first argument. And what about this one?
You can't negate two things.
Neg is a,
Unary.
it's what we would consider, it's what corresponds to a unary instruction for us.
Right.
Because you're going to have that same thing, right? You're going to have unary and non-unary instructions. Yeah. And what about this? Yeah, it's okay until it gets to the end, but now there's some extraneous characters at the end. So we're going to have to be able to detect this as an error also. So here's what happens when we do translate on this. Boom. And now look how this program is organized. When it goes through here, it's keeping track of these errors, right? And it says 9 errors were detected. Error on line 1. And look at these meaningful error messages that it gives. Isn't that nice for the user? Oh, there's one more error that we didn't notice here.
No sentiment.
There's no end. That corresponds to our dot end. Are you with me? So you see how these error messages all, second argument, not an identifier integer, comma expected after first argument, line must begin with the function identifier. Look how meaningful these are to the user. It doesn't just say syntax error. It tells the user what the programmer what the error was, right? Meaningful error messages. Right parentheses expected after argument, first argument not an identifier, right parentheses expected after argument, illegal trailing character. Oh wait, both of these had right parentheses. What about 7 and 9? Why was that?
Well, there is no 9.
1, 2, 3, 4, 5, 6, 7, 8.
Was 9 just an empty line for that?
Oh, I think the line, yeah, it was that empty line. Yeah.
That was the only one we dropped from 8 to 10.
Yeah. It's this empty line that it's flashing on right now. But two of them said right.
Oh, it's because we have the extra parameter in negative and neg. There should be a.
Oh, it's expecting the right paren here. Yeah. Once it got to, yeah. All right. Does everybody see how that works? Okay, and that concludes our demo.
So,
Okay, so on the slides here, we just have a repeat of what we saw in the demo. Okay, so here's the valid input, and then if the input is there's no errors, and we have object code and then a program listing. And then here's the same thing, the one that we just looked through with the errors. Okay. Actually, we're going to start doing a big code walkthrough for this, and we only have a few minutes, so why don't we just quit a few minutes early this time and call it quits. So we'll start off so we'll have the exam on Thursday. We will have on Monday. It would have been a little nicer to have gotten to the finite state machine for the parser today.
Can we have it do on Tuesday?
Oh, well, that was that sounded like that was all in unison. Yeah, you can do it on Tuesday. It's just a short written one. Yeah, let's do that.
Because then we can go through that.
And then by that point we will have gone through. You'll see how the parser and the lexical analyzer are connected, and how to. But I assume at this point now that you understand the two languages, these little toy languages that are just designed to teach you the language translation principles and for code generation. All right, good deal. Good luck on the test Thursday, and see you then and again on Monday. I won't see you guys out there in Videoland, but Thursday. But we'll see everybody on Monday. Okay.